fine. Okay, so what I'd like to do is to go over some of the basic principles that we have with inside hashing this week. Uh, so please ask any questions that you have as we go through the material, and then we'll have a look at the lab, and if you have any questions on that, and we might have a little look at some of the questions that we might ask in the exam. So does anybody have any questions to ask just now? Good. Okay, so let's just go ahead, and so please ask any questions that you have as we go through the material. And just let me see if I can share my desktop. And we want to share desktop. Okay, so hopefully you can all see that now. Okay, so we're into week 3, and we've done our basic ciphers and fundamentals. We moved on to symmetric key last week, and this week we do hashing and MAC. Okay, so next week we're doing public key encryption, so it gets a little bit tough. So there's maybe a bit of background reading that you might want to do, but I can give you a kind of heads up and the kind of things that you would want to look at in that, and then it should ease up a little bit when we look at key exchange. So we're still focusing on week 9 for our test, and I'll give you sample questions to do, and also a study guide. Okay, does anybody have any questions about the schedule, the timetable, what we're doing?
How deeply do we have to look at the math for the keys, the asymmetric keys? Because I done a unit a while ago where we had to do all the Euclidean math and actual paper.
No. To understand the basic principles behind it is enough. So we will look at RSA and how we generate the prime numbers and how we use that. It takes a bit of reading, and it's quite simple. You wouldn't believe how simple RSA is, but just to get your head around the basic process is the main thing. So we would only ever give very simple examples, and the main thing is really just trying to understand the basic process behind it. So it'll be clearer next week. So we find that that given a, a week or two to let it sink in, you'll find that most students will actually get the basic concepts behind creating a public and a private key. So we won't go into the depth for doing things like the Euclidean method. We might run a Python script to implement it, but we certainly wouldn't do it manually. If there's anything you need to do, you'll be able to do it very simply with simple numbers. Okay. Good. Okay, so this week it's hashing methods, and just let's see if I can find it there. Okay, so the key concepts are there that you should see. So the live lecture is here, and also the recorded lecture is also there. It's up to yourself which version of it you actually want to watch. The lab demonstration is here for the first part, and then someone asked if I could do a quick demo of the second part of the lab, so I've added that there. Any time if something doesn't quite, you don't quite understand something, then please say, and I'll try and do demos for these types of things. So you find a bit later on, I've got a demo here of Hashcat running with 8 GPUs. Okay, so so the basic concepts that we're looking at is the hashing methods. So it solves the problem where we can have any amount of data from 1 byte to a whole network, and we create a single signature for a fixed length signature. Typically, MD5 is 128 bits, SHA-1 is 160 bits, SHA-2 or SHA-256 is 256 bits, and SHA-512 is 512 bits. So we end up with a hex signature or a base 64 signature, and where we just change 1 bit, and it should completely change the signature that we have. Okay, so we can use various tools such as OpenSSL. It's a bit clunky to do it, so you're probably better with Python or Node.js to do your hashing methods, but certainly you can use OpenSSL to do that. So we typically use it in terms of fingerprinting our documents, our files on our system, to make sure that we can check the hash signature to see if the files have actually been changed. So we also see it in digital certificates where we have a thumbprint and a thumbprint algorithm. SHA-1 has been shown to be crackable, so Google took about a year and a half with 2 PDF documents. They managed to engineer the 2 PDF documents to have the same SHA-1 signature. It took a massive amount of computing power for that to happen, but it has started to ring alarm bells that SHA-1 is not just theoretically possible to crack, but possible. So SHA-1 is 160 bits for its signature, so that's kind of where the computational power is, that we can create what's called a collision within a reasonable time limit. You'll find that virtually no certificates on the web just now, on websites, is using SHA-1. So generally, as companies renew their certificates, they are going for SHA-256 or SHA-512. And we'll see it within our passwords. So Windows uses an NT hash based on MD4, that's before MD5, and we create a standard thumbprint for the password. We'll see it in Cisco configs. So we can see here, this is an MD5 hash with a little bit of salt in here, and this is extremely easy to crack. So if you have any routers or network devices, make sure that they're not using MD5 for their hashed value of the password. They should be encrypted at least and not using MD5. Okay, so the way that you crack a non-salted hash is with a rainbow table. So a rainbow table has pre-computed hash values for common words, and then all we have to do is to be able to search down the list until they're typically ordered in the hash, so we can very quickly find the hash value to match, and then from there we can look at the original word which created the password. We can also use a dictionary attack. So a dictionary takes a common dictionary words, and then on spec will then produce the hashes which we can then compare. The third method is to have a brute force attack, where we basically go from A, B, and so on. We go through the whole permutation of the possible words. As we'll see with Hashcat, it's quite easy to be able to target certain key sizes and certain common ways that people will do their passwords. The risk that we have if we don't salt our hashes, and this is the Adobe hack. 2 million, nearly 2 million people selected 1, 2, 3, 4, 5, 6. So given the opportunity for a 6-character password, if you don't constrain the user, then you can see the majority of users will go for the simplest possible passwords. The password checker measuring for entropy might actually think these are quite good passwords, but obviously they're not because they are well-known sequences. QWERTY looks to change quite a lot, but actually it's the first 5 characters on the top line of the keyboard. And we can see here people are using all ones. The problem with the Adobe hack was that they hadn't salted, so once the hash had been resolved back to the original plaintext, then every single one of the ciphertexts was cracked. So it was fairly easy to pick off common words from there. And then we got to worry that we have a jump off and I've been pawned. Then if somebody has used a password in the past and uses it for the same password for different accounts, then an intruder can jump off into other systems and then possibly even get back to their original core ID address, which resets virtually everything. Typically that's in a Gmail address or a Windows Live, and if they can get that, then that could be used to reset all of the accounts. Luckily, Google and Apple use multi-factor authentication with it out of band. So when someone changes a password, you'll find on a device that they have, you will see an authorization method coming through from them. Anybody any questions on that? Good. Okay, so we calculate our passwords, our strength. So we're taking a key space of 128 bits. So to give you some idea of what that looks like, and how many keys are possible. So if we print 2 to the power of 128, say, that's the number of hash signatures that are possible. If we take it up to 160, it's double, 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 and so on until we get that many. Okay, so even with an excellent hash cracker that's doing 100 billion cracks per second, to find it, you've got 1 in 37 zeros is the number of seconds. That's going to take you trillions and trillions of years to ever find a match. Unfortunately, what we do is that we typically generate the hash value from our passwords. So to understand the strength of the passwords, we will take for lowercase, for 7 characters, that's the number of passwords that we can have for lowercase and for uppercase, upper and lowercase, stat. And then if we add in other characters, say 10 additional characters, then we have that. Okay. So then if we want to calculate the time it's going to take to crack a 7-character upper lowercase at a hash cracker of 100 billion hashes tried every second, then you can see it's 10 seconds. 10 seconds for every single password to be tried. So you can see there that 7 characters are almost a non-starter. 100 gigahashes a second is fairly inexpensive, and you probably run it on a GPU on your your laptop. Obviously, with just lowercase, then it's 0.1 of a second. Okay, so we can calculate the strength that we have for our brute force. And we see just by adding one character significantly improves the security of it. 8 still doesn't look good. 9 looks a bit better, and we probably want to be starting about 10. So 10 lowercase is 1400 seconds. So that's the number of minutes, that's the number of hours, and that's the number of days. So we would probably try to see, that's 0.4 hours. That's 23 minutes for a 10 character lowercase. The big problem that we have is that most people will only select one uppercase letter and they'll put it at the start. So as we'll see from hashcat later, it can target that. When asked to put in a number or a character, most people will put it at the end, and then we'll repeat that character or we'll take it into a sequence. So even though that's our total time, actually we significantly reduce the key space or the hash space because we are fairly predictable in how we select our passwords. Okay, does anybody have a question about that? Good. Okay, so there's a whole lot of hashing methods. SHA-3 is the latest one. So SHA-3 is designed to be efficient for IoT, and it won the competition. And it's used in Ethereum and blockchain and IoT. It's energy efficient, it's fast, and it's fairly easy to implement on a limited processing power device. LM hash is used in Windows. Bcrypt is one of the slow methods, as we'll find, and there are various other ones. There are non-crypto hashing methods such as MER and FNV, which are extremely fast, even faster than MD5 and the SHA methods. A typical way that we would use a hashing method is with a key derivation function such as PBKDFS2 or bcrypt. We take a password that we know, say it's our hard disk that we're encrypting, password, we take a salt value, and then we feed it into our key derivation function, and that generates an encryption key for us. We then unencrypt our, in this case, the header of the disk, and reveal the actual encryption key, which has been used to encrypt our disk. Okay, the typical methods we use here are AES, 2FISH, 3DES. So the key that we generate here has got to be of the right length that would allow us to be able to use whatever key size of the symmetric key encryption that we actually use. PBKDFS2 is used in Wi-Fi. So if you're connecting just now through Wi-Fi at home with WPA2, then it's PBKDFS2, which is doing your core security. Unfortunately, it's easily crackable because of this three-way handshake that happens in WPA2, where we create a hash with PBKDFS2. If the user has used a fairly simple password in a dictionary, then we just have to compute it so that we can calculate the hash value that we see when a device connects to an access point. Anybody, any questions up to now? Good. So the way that we overcome the problem of rainbow tables is to use to use salt, it makes it a bit more difficult. So with this, we'll take our password and then we'll add a random value as a string, either at the start or the end, to the password, say, and then we'll hash that. So that the longer the salt that we get, the more permutations that we can actually have. Unfortunately, the salt needs to be stored typically beside the hash value, so that all an intruder has to do is to go through a dictionary and rebuild with the salt again and pre-compute the values or find a match, and then they can go through brute force because they have the salt. They'll just brute force, and with hashcat they might target for 8-character passwords with uppercase and so on. Okay, that's what a typical password storage looks like. The dollars differentiate the different fields. One identifies MD5, Fred identifies the salt that we're adding, and then this is the hashed password. So if we take password and add salt Fred onto it and hash it with MD5, this is the hash that we get. When the user logs in, they enter password. We take the salt from the password file and we add it together, and then we take a hash and then we compare the hash to the hash that we have. We can't reverse a hash back mathematically into its original password and salt. The only way we can do it is to perform the dictionary attack. So in OpenSSL, we can do this. We can add the salt ourselves, and then we can add our password, and it will produce an output there that we can check against. Okay, so here's an example here in our shadow file and etc. There's an MD5 hash, there's the salt, and there's the hash value. Then we can take the salt here, here, and then add the password, which has been used, Red Hat in this case, and we can see here that we create the same hash, so the user can now log in. The main problem that we have with hashing methods is that we can create a collision. It must be possible to take different amounts of data or different data inputs and create the same hash, because we've got an almost infinite amount of data that can go in, and we've got a finite number of hashes. The more hashes we have, the less chance we have of a collision. So we have what's called a collision attack, and it's fairly easy in MD5 to create a collision within seconds on a standard computer. In SHA-1, it's kind of theoretically possible in a reasonable time. Where we worry is that you have a similar context. Is it possible to take a message like hello with a hash and then another message which is in the context, which is goodbye, and produce the same hash? That creates a full context collision from there. Some methods are flawed. What should happen is that when you change one of the bits in the input, it should completely change the output. Unfortunately, if you flip a few bits in MD5, then you produce the same hash. The more modern methods, such as SHA-3, have been nearly proven to be secure against this type of thing, where all the bits can change, and we'll see a complete change in the hash output. And then it happened with this research that Nat spent 10 hours on the Amazon GPU cloud. It cost him less than $1. He used hashcat using the CUDA infrastructure, and he managed to produce the same hash signature for 2 images. So basically he stuffed bytes into both images, and because of the birthday attack, it is possible within a reasonable amount of time to actually come up with the same hashed value for it. He continued the work and he did it with 3 images. He produced the same MD5 signature. Okay, so that shows you the power of our cracking infrastructure. So obviously many of our passwords are stored on Windows machines. So this is what a Windows user ID looks like. So this is the domain ID that we have, and the ID at the end is the user. So 500 is the admin. The first user starts at 1000, and so on. The passwords themselves on a non-domain network, so on a standalone computer at home, the passwords are contained in the SAM hive, and these contain all the hashed passwords on the system and the usernames. And a Windows domain controller, as you would find at work, the domain controller has these, and the local machine shouldn't have a copy of them. So these files are protected when the system.
Sorry, but usually on a domain, I believe that if you log into one of the machines, your password should be cached on that device, but I'm not sure if it is stored in a way where we can crack it or not. Uh, I don't know about that.
Yeah, yeah. I mean, certainly the passwords are set up on the domain controller, and I would assume it would be the security of the end device, whether it cached the passwords. Obviously, it's a security risk if it stores it in the registry or in the files on the local machine, especially if many users were using that machine. So it's
Yeah.
something to maybe investigate.
Well, I'm saying that because let's say if you are disconnected of the domain and you try to connect to your device, you still be able to log in.
Only if there's a local user set up. So you shouldn't be allowed to log in. So that would be a security hazard, because somebody could disconnect the network cable and then log into the local machine. So I think it's typically local users that are set up as static. I wouldn't think that you should be allowed to connect if you can't connect to domain server. If the domain server goes down, then you shouldn't be able to log into a computer unless it's set up so that you have local rights.
I suppose that refers probably to domain laptops and such like, though, doesn't it? Where someone maybe goes home with a laptop, but they use a domain account to authenticate.
That's right, but they should still connect to the domain server to be able to get the rights. But it's probably been set up so there is a local user that they can actually use. But in a domain setup, you shouldn't have any rights to the local machine, and it's probably just the way that it's set up. It just needs to be set up more as a standalone machine. But if you want the power of a domain server, you shouldn't be able to allow to be access any files on the machine, even if you're disconnected from the network.
I guess it's really a question of usability. In my organization, it's definitely when you log in from a laptop the first time, then your user profile is stored locally, and you can log in with the same profile later without internet connection.
Yeah, yeah. I think it all depends on what the setup is, especially with laptops. You want that flexibility, but on standalone machines, probably you don't want that, and you don't want anybody connecting into a local machine. Okay, so so you should find if you cold boot a disk, then it takes the protection off the config folder, and within there you'll find the SAM file, which has the hashed passwords on it, and then we can use SAM to dump or BK Hive to extract that, and it gives you this format here. So this format here is in the form of an LM hash and an NTLM hash. That's what it looks like: user ID, LM hash, NTLM hash. some comments and so on. So John, the Ripper, knows this format and will generally try to crack either one of them. And you can see in this case it's fairly easy. It's found Napier here, and it took no time at all to do that. We can also use offcrack to do this. Offcrack is quite good for rainbow tables. It's got a graphical interface which you might find useful, and it can take different sizes of rainbow tables. Obviously, you can have massive, almost terabytes of rainbow tables, but if the values are salted, then it doesn't do any good at all. It's just going to do the same as John the Ripper, and you're going to have an overhead in there. What you definitely need is a GPU infrastructure there to speed things up. And that's what the GPU infrastructure looks like. So each of these GPUs typically has about 4,000 cores in them, and you can give each of the cores a certain part of the key space or a certain number of passwords to look at, and they'll run in parallel. And you also get multiple threads. So these processors are multi-threaded too. So you might have 25 GPUs with 4,000 cores, but you can actually run many more threads on each of the GPUs. So they're highly optimized system. This one here cracks an NTLM hash within 5 hours for 8 characters, and a 14-character password in 6 minutes. Does about 350 billion hashes a second, and you can see the cost is fairly low from there. They're typically used in Bitcoin mining, but they're also used in hash cracking. So they vary. We vary in terms of the performance of the hashing. You have the ultra fast ones, such as Murmur, as we saw. The really fast ones, such as SHA, then to SHA-3, and then it goes right down to PBK DFS2. We can make it go as slow as you want. There's a compromise between, if you make it too slow, it's going to cost you computation power whenever a user logs in, and there might be a delay in there too. And the ultra slow ones are here. Bcrypt, very slow. Oracle 10, APR1, and so on are extremely slow methods. So just let me see if I can find my presentation. So we can do a basic benchmark for the for this with Hashcat. Just let me do that. So I just got a little online tool for my server. I've just taken a message here, and this is the real-time hashing that it's doing for this. So you can see these are really fast. Bcrypt is down at 215. I have 5 rounds of Bcrypt. If I add an extra round, it halves the hash rate, and obviously it's more difficult for a cracker to be able to crack these, because in Oracle 10 it's only going to try 114 dictionary words at a time, and it's going to take a long time to crack these ones. Whereas if we use Murmur or SHA, we're up at 120,000 hashes per second. This is with a non-GPU device here. Okay, so if you're interested, that's the basic Python code. I think it's at the end of the tutorial. You can run that yourself. I think you should be able to get most of the libraries. They're typically coming in from this passlib.hash, and you should get most of the hashes in there. I think with Bcrypt you've got to install something else, but I think we installed that already on the machine. We use a standard salt. In some cases, some hashing methods need longer salt, so we're setting that up then. Okay, anybody, any questions about that? So we use so we can run our basic benchmark with hashcat -b. We're not using the GPU here. In this case, our virtual machine is using a Xeon single core. If you had a GPU, it would show you that you had a GPU in there and whether you're using CUDA. So even in our cloud, we're getting 46 mega hashes for MD5. So we can try 46 million hashes on a single core. If we had other ones, other cores that would run faster, PBK DFS2, 1,800 hashes, a massive difference. NTLM for Windows, it's up nearly 100 million hashes that we get in them. Okay, so if possible, we want to be able to make sure that we make it as difficult as possible to crack, but don't make it too difficult when the user actually logs in. Okay, does anybody have any questions on that? Good. Okay, then for Mac, what we can do is that, so an attack is where somebody starts a conversation and then an intruder comes along and kicks them off, and then is then able to take over the connection. We can overcome that by having HMAC, where the sender and the receiver agree on a secret key at the start of the conversation or predefined in some way, and then what we do is that we use that key to be able to create a hashed signed hash signature. On the other end, the other side takes the same secret key and takes the message and does a hash of it and checks that the HMAC messages are the same. So we can use different sizes, HMAC, MD5, SHA-1, and so on. Okay, so in this case we need both a generating key and the hash signature. Another thing that's increasingly used is our one-time passwords. So if we take a hash of an original seed that we agree to, and then hash that value, hash it again, and then start later on, then only by knowing the original seed is it possible for you to create the next hashed value in the sequence. So this is often used to get access to servers and so on. Rather than having passwords, you will actually have a key fob that will generate the next hashed value for you the next time you log in. You can also have a timed password, where the password is only relevant for a certain amount of time, such as 5 seconds. So you have 5 seconds to use that hashed value. If you don't, then it will change to the next time. And you can also have a counter, so you can count the values on, or you could be challenged with a certain counter value, and you've got to produce the hash of it. Okay, so we've got demos of that type of approach online, but it's often a much better approach than having just passwords on a system. And you'll see a lot of people with RASA key fobs that will generate these one-time logins. Google Authenticator certainly uses it. Okay, does anybody have any questions on what we've covered? No. Good. So what we'll do is we'll have a look at the lab. from here. Okay, so the important thing is just for you to be introduced to some of the hashing methods, and also to look at the basic cracking methods, which is Hashcat and John the Ripper, and how they're actually used from there. So hopefully you will be able to find the uh, text values in these hash signatures. And then from this one, did everybody get this one correct? We pop off the salt. We try the words. And we should be able to get the same hash here. Did anybody any questions about how that one is done? Everybody got that one okay?
I'm not sure many of us have had the chance to try it yet, with the lectures being released, the lecture video being released only yesterday.
Okay. Right, so I'll just show you how to do that one then. Hopefully this is going to paste okay. In fact, I think look code. Into in a minute. So that's E4. Sorry, that's just got the text. So I just paste that. Okay, so the first one is WA to there is the salt. Go here, paste that in. And just check that that's right. Okay, so we'll try Napier, and we're looking for a hash value that begins with J. Oops. I need another space in there. So that starts with JD. So that's the right password. So the password here is Napier. So for each one, you go through and you pop off the salt between the dollars. Make sure you get the hashing method correct. So I'm using APR1, but for this one here, we're using MD5. So we would change that to -1, and we take the salt and we try each of the passwords until we get the hashing value. Does anybody have any questions about that? Good. Okay, so for this one, when you download the files, just check the MD5 hash and see which one has changed. It's a typical way that we do it. If we're downloading some software, we would just do a quick check of the hash, and if it doesn't equate, then we wouldn't trust it. A6 has two PostScript files which have completely different messages in them. So you should find you've got a PostScript viewer on your Linux, your Ubuntu machine. Just go to the file viewer and double click on both of them, and you'll see the different letters. But when you do your MD5 checking, you'll find that they both have the same MD5 hash signature. So there are tools online allow you to take files, documents, programs, and to produce the same hash signature. So although you see a download program with, say, a zip file, and it shows you the MD5 signature, you can't necessarily trust it because somebody could have actually created another zip file that has the same MD5 signature in there. So this one shows you a collision. So as I showed you before, you can do a benchmark on Hashcat to benchmark your system, and you can also run. You can also just benchmark for specific methods. So 0 is MD5. So you go and find the hashing methods that you need. Typically, you just use grep. Yeah. I need to find my pipe. And then you'll see the number that you've got that will give you the hashing methods. So there are thousands. There's many different hashing values that you can have for it. But a 0 for the -m is MD5. So we can benchmark that on its own. And this won't run the whole benchmark. It will only benchmark MD5. So we can see that we've got 46 million hashes per second. Okay. So then for the next one, we're using Hashcat. We create our file and we create our words list. So the words lists are these, and then we target MD5 because this looks like MD5. It's no guarantee because it might be other hashing methods, but you're told it's MD5. You attack it with 0, which is MD5, and then you should be able to crack these ones very quickly because it's just using your own dictionary. Then any questions? Oh, good. And then this one, you create a list with common fruits in it, in a words list. They should be in lowercase, so it's lemon and banana and apple and orange and so on. And then just go through and see if you can find the common fruits that are in there.
Sorry, Bill. So when I did this, I always saw the answer as capital letters. All the letters are capitals.
Yeah, so it can be an NTLM hash because those hashes are non-case sensitive for an LM hash, so it converts it to uppercase.
So let's say if we are trying to find a password, there is a chance that we will never find it because it is showing the password as, let's say, capital letters, all of them.
No, it should actually identify it properly with its upper and lowercase. It's just that some hashing methods convert it, so it doesn't matter if you put it in an upper and lowercase. But the hash of an all uppercase password is completely different from all lowercase. So what to do is to try these values with the word that you find. Try to hash to see if it's all uppercase or all lowercase.
Okay.
Okay. So then 1400 is SHA-1, as we saw. You do the help manual and you should be able to get the number for it. But SHA-256 is 1400. And these ones are the NTLM, and that's 1000, and you should be able to crack those ones. Again, create, this looks like SHA-256 I think, just so you can count the characters, and then you would target SHA-256, create a list of football teams in Scotland, and then hopefully you should be able to crack those ones. But the real power of Hashcat is when you use a rule, and with a rule you target, in this case, 8 characters, so that you know that you have 8 characters, so it doesn't possibly target 9 or 10 or 5. You would target 8 here, and all lowercase. The increment means that you go from A, B, C, and then AA, BB, AB, and so on, up to the 8 characters. If we didn't put the increment, it will go from 8 A's, and then 7 A's and a B, and so on. So the minus increment kind of builds up the tree. And I think in these cases, the words are either 3 or 4 characters long. So we crack this hash that should be almost impossible to crack within less than a second. I don't know if anybody's tried that one yet. But it's the A minus 3 will do this brute force for us with a rule.
I did it. It worked.
That's good. Yeah, face, eye, was that one of them? Yeah, if you take away the increment,
Yes.
it's going to take a long time to do that, as we calculated before, unless you have a GPU. So it comes up and says, do you want to continue? I just Control C, because it's going to take a long time. That's why you need the increment flag. And then we can target one letter as lowercase, uppercase, or a number. So in this one here, we know the first characters are password, and then it'll go through and try a lowercase at the end, an uppercase, and then a number at the end. Okay, and you should be able to crack those ones. And then John the Ripper has its own sort of inbuilt library for dictionary for these things, and you should be able to, as we saw, this is the Windows dump that we get, and John the Ripper should be able to go in and crack those if we give it the names of fruits. Then we've got some code for the LM hash, if you want to give that a try. APR1, 2, and there's the SHA. PBKDFS2, again, there's this passlib.hash that you can integrate, and you can add the salt value. Probably this is the most reliable code that you can get, that you can trust. If you ever want to create your own hash values. If you're interested, we've set up a page which is pure JavaScript here. Let's find where that is. Try and find crypto.js. So this should work from your mobile phone. So you can now do crypto on your device, and we're just running some JavaScript code to give us our hash functions here. Under the MD5, the Mac, HMac, where we're using the password to generate our key. Okay, so this should be fairly reliable, but make sure you do check your hashing values against something else, and maybe look at standard test vectors that you can use to make sure your hashes are working correctly. Okay, so lab again. So there's a demo of the lab here, and there's also a demo of the second part of the lab. And don't get stuck on any specific bits. If you can't get it done, then try a few things and then just get in contact with us and we'll try and help. So there's bcrypt.
Sorry, Bill. Can for G1, I have a question about G1. So you're asking for the value of salt. So I get the values, but like it is really long, and I don't know which one is the salt because there is lots of dollar signs. There is more than two. So I didn't know which one is the salt.
This is salt.
Yeah, but you're asking for the value in hash.
Yeah. So just identify maybe a couple of characters. So for this, does it look? I'll try and find where there's a result. Let's bcrypt. Can you spot it there? Is it this one?
Yeah, so my values are totally different.
So you should see the hashing method, then you should see the number of rounds, then you'll see the salt, and then you'll see the hashed value.
Oh, okay, yeah. So I do see the number of rounds, and then so they are between $2, and then the salt is between another $2.
Yeah,
I think that's it then. Okay,
yeah.
thank you.
So there's lots of different formats. If you want, you can. I tried to gather together all of the hashing methods that are almost possible, and you can run it from this Python script. Some you need to truncate the salt to just 2 characters, and other one 22 characters. So you just got to get the salt quite right. But I think this one here should give you the bcrypt, and the other one ppk, and you can add the number of rounds. By default, it's probably just giving you the default value, but if you want to make it more difficult to produce the hash, you can keep increasing the number of rounds.
You see, you just selected column 22 between brackets. I didn't understand what is that 22.
So that's Python truncating or extending to 22 characters.
Okay.
If you put the wrong salt length, then it complains quite rightly. Let's see, I can get that one to run. Is it G?
It is H.
Is it this one here? Okay, so you can see the identifier is there. That's the rounds there.
Yeah.
And then the hash is after it, and you can see there's 2 different formats there. Okay.
Okay. Thank you.
So you can give it a try, but you'll find it's very slow because it's meant to be slow. So the 3 key derivation functions are bcrypt, PBK DFS2 and script. There's a little bit on the 8 Mac, and if you want, you can run there. You can also download the Battlefield hash list and try it against the RockU list to see if Hashcat can crack for these MD5 passwords. Anybody? Any questions? So I appreciate you're not all on this lab yet, so don't have any problems in asking, even though the labs are maybe like a week or two old. If you're still on that one, then please just ask and don't just stick to the latest lab. Okay. Remember to use Slack to ask a question at any time and to share your knowledge. Okay, if you're really interested, I used an 8 GPU cluster. I think it costs about $8 an hour, and so if I just pause there, just pause back a little bit, you'll see there. So when we do our benchmark, so you can see we've got the Tesla GPUs in there. You've got to have good cooling on these devices. That's what they look like, and they can get very hot because they're running very fast. And this one has nearly 5,000 CUDA cores in it, 2.9 teraflops. So they're highly optimized. Some of the latest research is looking to be able to crash these devices so that it stops people from cracking the passwords, because you overflow the memory of them, because they're obviously limited in the memory that each has in them. You often have to delete the pot file, because once Hashcat is cracked something, it puts it in a little cache area. So if you want to restart it again, you delete that pot file. And so you might, if you've installed it on Ubuntu, you need to do the ---- force to make it run without a GPU infrastructure underneath. It just kind of complains a little bit. And then this should show us.
Sorry, in couple of questions there was like how we found how many I think tries it took to find the answer. I couldn't find where I can read this information.
Yeah, I'll just show you that in a minute.
Thank you.
So you can see here, there's the GPUs that are in there, and hopefully we should be able to get a benchmark for that. So that shows the GPUs that we have. So that's 8, but you can also get a 16 GPU cloud. I think that costs about $15 an hour. So this should show us what our benchmark is for these GPUs. It's taking a little minute to initialize them, but we should be able to get giga hashes. So that's 5 giga hash per GPU for MD5. So that's 5 billion hashes per second, and then we have 8 of them. So that's 40 giga hashes per second. That covers most dictionaries. And if we use Hashcat, we can target. So the question was, when we do that, so in this case, we're taking a hash, and then I just see what the word is. It's got 5 letters. Yeah. And so by brute force that would be 26 to the power of 5. But it'll stop once it finds the hash. So because it begins with H, then it won't even get halfway. So then when we run it with that rule, you should see it trying. So we run here. This should be fairly easy for it to crack. And it shows for each core, so only one core has been used here, and it defines the number of guesses. So there's the progress, that's the total number, and that's the number that it found it. So it's only taken 12% of the total space. So it's what is that, 3, is that 1.1 million possible, but it only had to search through 1.4 million. I think that's 11 million hashes, and it did it in 1.4 million, so it only did 12.5% on a single core. You see in that example, it didn't even initialize the other cores. So did everybody see how that was done? Okay, so it's showing you here. So progress that's the total number here, and it found it here, and it searched 28% of the space and stopped. This time it was using all of its cores, and these are the ranges. It splits it into 8 and then gives each core a range. One of the cores finds it and then tells the rest, and then they just stop. Any questions? So it goes up, and we go right up to hello you 1 2 3, which is 1 2 3 4 5 6 7 8 9 10 11. That's 11, and all we're doing with the last one there is to make the first letter uppercase, the rest lowercase, and then numbers at the end. And I think you'll find that it gets cracked fairly quickly. Even though we said 11 characters were going to take a long time, actually it doesn't take too much if we create a rule which is uppercase at the start. And so this is uppercase, lowercase, that's 9 characters, and it finds almost straight away. And the very last one, the rule we use is uppercase, lowercase, and then 3 digits at the end, 12 characters. 12 characters. And it took virtually no time there for that. Okay, so by targeting, it becomes much easier to crack it, especially focusing on like 8 lowercase, first one uppercase, and then the last one to be digits. We can also look at changing an O to a 0, a 3 to an E, and so on. The standard things that many people will do. Hashcat can target that with its rules. Any questions? No. So when you've got time, have a look at some of the sample questions. I'm not expecting you to go through all of these. This is an interesting statement around the Yahoo hack. If you dig in, look, they said that the vast majority of their passwords were in bcrypt, but some weren't. So it's very difficult to read the incident report and find out if they had said that all of the passwords would be bcrypt and were actually quite tough to crack, then it might have been might have looked better on Yahoo if that was the case. But many companies have older passwords using old hashing methods or fast hashing methods, and then anybody who upgrades is then giving a bcrypt password, but there's still 2 levels of hashing going on, which means that the older passwords are weak. Any questions? No? Does anybody have any other questions at all about where we are?
Hi, Bill. I have a question, a bit off topic, but is there any room in the lecture theater if I decide to attend some of the lectures?
Yeah, very much. Yeah.
Oh,
There's
lovely.
lots of spaces. Just come along. Are you based locally?
I am in Glasgow.
Yeah, it's not too far. So come along 1 o'clock on a Friday, and we have a lab at 3 o'clock. So if you wanted to come along and just chat in the lab too, then that's fine. Maybe talk to some of the campus-based students too.
Yeah, I'll definitely come. Not this week, but some of the next week. I will come and see you.
Great, excellent. Any other questions? Nope. Good. Okay, so remember to use Slack, and if you're emailing me, remember to use the module number in the subject field. If you've not got your VMs up to now, then email me and we'll get them created within a day or so. If you want advice on setting up your own VM environment, then please ask, and it's a good thing to do just in case our cloud goes down. So just keep asking questions as you go along, and just anything that doesn't quite go in, then please ask. The more questions that you ask, the more that we know where we can plug gaps. Okay, well, thanks very much, and I appreciate all your hard work.
Sorry, Bill, can I ask one last question? Sorry, I took all the questions today. I have a question about the salt in Node.js. In the lab 2, in the stream ciphers in Cha-Cha 20. So you asked what is the salt, how many bits will the salt use? This is in lab 2.
Yeah, so is it RC4 or is it Cha-Cha?
Cha-Cha 20.
Yeah, Cha-Cha 20, I think the salt size and it says the key the just give me a minute. So standard test vectors are these. So these are taken from the spec. That's the key, which is 120 bit there, and then that's the nonce or the salt. So if you just count and multiply that by 4, that should give you the salt size. There's various nonce ones there. 8.
Why we multiply it by 4?
Because these are hex.
Okay.
Sorry, these are These are hex values, yeah. So this is a hex. It's a hex stream. So the key is defined in hex there. So before this, you would use a password key derivation function to take your password and convert it into a hex stream. You can see the nonce or the salt is a hex value. That's typically generated on the system randomly, but obviously to test your key stream, you would manually put it in. So it's 32 bits.
Okay, thank you.
Chacha is used extensively now. OpenSSL. If you use SSH, you probably find it's Chacha 20 that's doing the encryption.
Thank you.
Okay, thank you. Anyone else? Good. Right. Okay. Well, next week is public key encryption, and if you want to kind of have a quick look before the lecture, is fine. But I'll go over the basic principles next week, and we'll keep it nice and simple, and we'll try and understand RSA and elliptic curve methods. Elliptic curve is just taking off everywhere just now, and it's used extensively for security, especially in Tor networks and Bitcoin, blockchain, things like that. Okay, well, thank you very much, and I'll speak to you next week. Okay, bye-bye.
Thank you, Bill. Bye.
Okay, bye-bye.
Thank you. Bye.